Exchange Rate Prediction Project. Hello, my name is Evrim. Today I would like to present you my project that I prepared for Regis University Master of Science Data Science Practicum. I am coming from a background of economics and finance, considering that I picked a subject to my project that I can provide some basic information regarding the field besides the other technical information that I will share. This project is a combination of machine learning and financial time series. Financial time series are nonlinear and non-stationary structures, meaning they are non-directional and ever-changing without presenting any regularity. In general, machine learning and more precisely deep learning applications are highly successful to map such irregular data, and in this project I have chosen sterling US dollar rate to represent the financial time series. Even though machine learning methods are successful with irregular data, studies show that classical econometric methods are known to outperform more sophisticated methods on average, especially for univariate time series. As a note, time series analysis has two main structural approaches, univariate and multivariate. The methods using the response variable, the variable that we are trying to predict, as its own predictor, and this is called univariate. Alternatively, when we use other metrics for the prediction, that is a multivariate analysis, and during this project I tried to illustrate both approaches. For the univariate analysis, the literature suggests ETS or ARIMA methods, and I picked ARIMA. But before starting to explain that, I would like to talk about the pre-processing of my data a little bit. As a starter, I collected my data first, so my resources are as follows. I have collected all my exchange rate data from Federal Reserve, not only the GBP, meaning sterling data, but also the other provided exchange rates as well. Including this, all my data was collected as CSV files. Excel is used to delete some useless rows and columns, but all of the data cleaning and processing is done on Python in this notebook. I preferred using notebook due to the step-by-step functionality of them. My second data source was Federal Reserve Bank of St. Louis. I have LIBOR interest rates and normalized GDP data from here. Lastly, I acquired current account to GDP data from OECD website. At this phase, I organize my data in a way that I can use during my analysis. First, I organize my exchange rate data. This one needed the most cleaning among them, and they were provided daily. Second, I cleaned and integrated the GDP data to Forex, which stands for foreign exchange rate, and this GDP data was monthly. Also, I interpolated them to the daily data. Third one was the current account to GDP data. Similarly, I needed to interpolate them from quarterly to daily data for an appropriate matchup. The fourth and the last one was LIBOR rates, which were provided daily. And after merging all these data, I saved them to a CSV, and for further analysis, I pulled the data from this file. Eventually, the data became 29 columns representing features, plus date information, and 4,920 rows representing the observations. Let's start to our analysis with some basic information. After reading the data from the file, my response variable, the one that I will be trying to predict, which is sterling US dollar rate, looks like this. This data is from the beginning of 2001 and it goes until 2020 August. As you may observe from the chart, the rate fluctuates between 1.2 and 2.2, indicating that depending on the time period, a sterling can buy from $1.2 to $2.2. My baseline model that I will be comparing the success of the deep learning methods is ARIMA. ARIMA stands for Autoregressive Integrated Moving Average, and it has three main elements. The first one is I component, and it means integrated. We start with a statistical test providing the stationarity, non-stationarity information. Augmented Dickey-Fuller test. Literature suggests that a statistical analysis can be conducted if the series is stationary. We know that the financial data are non-stationary, and the test confirms that fact. In order to make a series stationary, we have to take differences of the observations. until the series gets stationary. We get that level with the first difference, and this is the I part of the ARIMA process. As we may observe now, the series is not ever changing, but of course it is full of white noise on a linear path. There are two excessive movements that can attract our interest here. First one is around 2008, which is the time for submortgage financial crisis, and the second one at 2016, 24 June, which is the day after Brexit referendum. It is quite understandable why these periods are so much volatile. The second, AR, referring to autoregressive, and third, MA, referring to moving average, can be examined together. Here, with the literature suggested tests, we decide the levels of them at the same time. I do not want to get into the technical details of this due to the complexity of the matter, yet by looking at these graphs, we can tell that an ARIMA 111 process is what we are after. First and last ones representing AR and MA levels, whereas the middle one representing the difference level. After the application of the process to the series, we can observe that the residuals, errors from the actual values, are forming a normal distribution, which confirms that we have done our job in this ARIMA process correctly. When we apply the process to our series' test data, which I separated the last 50 elements of the series for it, we get the following graph, a comparison to the actual values. Our evaluation criteria will be RMSE, root mean square of the errors, which is one of the mostly used evaluation metric for the time series data. We see that 0.00643 is the score. As a note, the lower the metric, better the prediction is. When we come to the machine learning methods applied in this project, the first one is multi-layer perceptron for univariate analysis. Similar to the baseline model, we read our data from the file first. Different than the ARIMA process, we have to process our data furthermore for neural networks. Since this is a univariate analysis, the data must predict itself. But of course, we cannot use today's data to predict today. We should be using yesterday's data to predict today and today's data to predict tomorrow. In a sense, we will be using the same data shifted, a lagged value of itself. Obviously, we can use a data that is 2 or 3 or more days earlier. This is a level that we decide for the lagged value. I will be predicting 50 days data. Thus, I prefer to use a lag value for 50 days. This is the function that will help us to formulate the lagged values. After organizing the data and separating the test group, we can run our model. As an extra effort, I have written an activation function called swish. It is a relatively newly proposed activation function by Google Brain Team, and it tends to work better than usual functions. I will be using it in my models, hoping that it could provide better approximations and thus mapping. Finally, the RMSE metric result for this model is 0.05807. Interestingly, there is an important gap between the predictions and the actual values. If we can shift the predictions down, it could be a good match, yet it cannot be done for the future values that we have not seen yet. The second model is the univariate prediction with CNN architecture. After a similar process to the previous one, with little changes, we run our model and get a better mapping and match with the actual values this time. The evaluation metric value is 0.01911, 3 times better than the previous actually, yet way behind the ARIMA model. My third model is the MLP architecture, but this time with the multivariate analysis. In this process, I use all the data that I gathered for the project, with the hope to acquire better results. I lower the lagged values to 5 from 50 comparing to the previous models. Yet, there are 28 more variables in the equation, 22 of them being other exchange rates, and the rest are main macroeconomic indicators for both country US and UK. Even though it is trickier than univariate models, with so many variables, the prediction values get smoother. The evaluation value for RMSE is also a tad bit better, 0.01308. My last model in this project is for multivariate analysis with CNN architecture. In origin, CNN architecture is designed to grasp features from images to be employed for image recognition, yet shows remarkable capability to extract features from sequence data as well. Time series, being a sequence data, provides a good opportunity to test CNN architecture's abilities. However, this model does not get as successful as the univariate peer. The RMSE metric is 0.02954. I believe an alternative could be feeding the different groups of variables separately to the CNN architecture by using functional API. It is a useful tool, especially in such cases where different variables are presented and affecting the response in different ways. When we compare the results, we can see that the literature findings are correct. The Bayes model for the prediction has the best metric by far. While the results of the Bayes model is 0.00643, the closest result to that one is 0.01308 from the MLP architecture with multivariable prediction process. Then comes the CNN univariate prediction process with 0.01911 and the CNN multivariate process with 0.02954 thereafter. The MLP univariate process has the worst score with 0.05807. A small reminder is needed regarding these results as well. The ARIMA process is a linear regressor, thus the results of the process would be the same even if repeated again. Yet that cannot be told for the deep learning processes. In all of these deep learning processes, random factors are used. Therefore, the results of each process change each time it runs. Whereas it can get better, it is similarly probable that they can get worse. While I'm coming to the end of my presentation, I would like to be thanking you wholeheartedly for listening this relatively long presentation. Though I have to mention some of my references first and recognize them. Majorly and thankfully, I referred to Jason Brownlee's instructions numerous times. His books, website, machinelearningmastery.com, teaching and tricks. I utilized them happily. I guess I could have not finished this project without his aidance. Along with that, all the libraries, packages, and modules that I used were great gifts to me, to all the people who uses them and benefits them. I have learned so much by referring to their documentations excessively. And lastly, for all the small hiccups and issues, there was Stack Overflow and the community that shares willingly and vigorously. A special thanks to you, bearing with me, and to my instructor Christy Pearson, helping me along the way with her guidance, providing a great support and with her welcoming smile. All the best. Thank you.